Imagine oceans retreating, ecosystems collapsing, and life vanishing across the planet. This truly happened on Earth. Long before dinosaurs or forests, Earth faced one of its most devastating biological disasters. Many believe the dinosaur-killing asteroid caused the worst extinction. That assumption is wrong. That famous event was neither the deadliest nor even the second worst in Earth's history. The true catastrophe occurred far earlier, in a world almost unrecognizable to us today. Scientists call such global collapses mass extinctions, wiping out at least 75% of species. Over the last 500 million years, Earth has endured 5 mass extinctions, known as the Big Five. Among them, one stands out as both the earliest and one of the most lethal. This event is the Late Ordovician mass extinction, a disaster that nearly reshaped life itself. To understand it, we must travel back more than 445 million years into Earth's past. Welcome to the Ordovician Period, which began about 486 million years ago. At this time, Earth was almost a water world dominated by vast global oceans. Sea levels were extremely high, rising over 2,000 feet, or about 600 meters, above today's levels. Continents were fragmented into small, isolated islands scattered across shallow seas. The global climate was warm, humid, and filled with constant oceanic evaporation. With such conditions, land should have thrived. Instead, it remained almost empty. There were no trees, no grass, and no complex animals living on land. Only simple plants, resembling mosses and lichens, survived near moist shorelines. While land stayed quiet, the oceans became the true center of life. Marine life was experiencing one of the greatest evolutionary explosions in history. Strange, unfamiliar creatures filled the seas, unlike anything alive today. This explosion was driven by a structure still vital today: coral reefs. During the Ordovician, corals expanded rapidly, forming massive global reef systems. These reefs created new habitats, allowing countless species to evolve and diversify. But this thriving alien ocean stood unknowingly at the edge of total destruction. Hidden within these reefs, entirely new predators emerged, reshaping food chains across the Ordovician oceans. Among the most formidable were endocerids, an extinct group of straight, plate-shelled cephalopods. Unlike modern squid or octopus, endocerids possessed massive, rigid shells for buoyancy control. Some species reached lengths of nearly 30 feet, or about 9.14 meters, excluding their soft bodies. Their total body length may have been even longer, making them the largest animals of their time. Some researchers estimate the largest individuals weighed over 2,000 pounds, or about 1 ton. Armed with powerful tentacles and sharp beaks, endocerids were likely apex predators. They hunted near the seafloor, targeting slower or poorly protected animals. One of their most common prey were trilobites, among the most successful animals in Earth's history. Trilobites had already existed for millions of years and diversified into thousands of forms. To date, scientists have identified over 22,000 distinct trilobite species. They occupied nearly every marine environment, from shallow reefs to deep ocean floors. Some species even ventured briefly onto land during wet conditions. Despite their success, trilobites faced constant danger from increasingly efficient predators. Among these were eurypterids, commonly known as sea scorpions. Eurypterids were highly diverse, with limbs adapted for grasping, swimming, or tearing prey apart. Their tails varied as well, some shaped like paddles, others ending in piercing spikes. During the Ordovician, most eurypterids were small, but dangerous exceptions already existed. Some individuals reached human-sized lengths and likely ranked as apex predators. Fossilized species reveal diets including jawless fish, trilobites, and even other eurypterids. This makes eurypterids among the earliest known cannibalistic predators in Earth's oceans. And these were not the only nightmares lurking beneath Ordovician waves. Eel-like conodons swam through every water layer, armed with incredibly sharp tooth elements. Their teeth were among the sharpest ever evolved, thinner than a human hair. In this crowded, predator-filled ocean, life thrived, but balance was dangerously fragile. Yet even these predators shared the oceans with creatures stranger than anything alive today. Among the strangest were radiodons, a highly diverse group of early arthropods. Radiodons evolved into predators, filter feeders, scavengers, and sediment sifters. Their bodies bore paired frontal appendages used to grasp, slice, or trap prey. Some radiodons hunted actively, while others fed passively in open water. This flexibility allowed radiodons to spread across many ecological natures. One extraordinary radiodon dominated offshore waters during the Ordovician. Its name was Aegirocasis, a giant filter feeder unlike typical predators. Aegirocasis reached lengths exceeding 6.6 feet, or about 2 meters. Instead of killing prey, it filtered enormous volumes of water for plankton. This shows Ordovician seas supported both giant predators and giant filter feeders. Life had diversified to an unprecedented level beneath the waves. But extreme diversity can also make ecosystems dangerously sensitive to change. Many species depended on narrow temperature ranges and stable sea levels. Reef systems, in particular, required warm, shallow, well-lit waters to survive. Even small environmental shifts could disrupt these carefully balanced habitats. And while life flourished below, the planet itself was quietly changing. Tectonic plates continued to drift, slowly rearranging oceans and continents. These movements altered ocean circulation and long-term climate patterns. At the same time, atmospheric chemistry was beginning to shift. Carbon dioxide levels gradually declined, reducing Earth's greenhouse effect. For now, the oceans remained warm and life continued to thrive. But the conditions that sustained this alien world were slowly slipping away. A global transformation was approaching, unseen but inevitable. And soon, the oceans that nurtured life would become instruments of mass death. The coming catastrophe was not driven by biology alone. Forces from space also played a role. During the Ordovician, Earth experienced an unusually intense period of meteorite bombardment. Evidence comes from Ordovician rocks rich in L-chondrite meteorite fragments. These meteorites suggest a large asteroid was shattered somewhere in the inner solar system. Many scientists believe Earth's gravity helped pull this debris into near-Earth space. Some models suggest these fragments formed a temporary ring around the planet. If true, the Ordovician sky may have looked dramatically different from today's. Meteor showers would have been frequent, intense, and visible across the globe. This bombardment lasted for millions of years, not days or centuries. Impact rates may have been up to 100 times higher than modern levels. Most impacts struck the oceans, disturbing marine environments repeatedly. Shockwaves, tsunamis, and debris clouds would have stressed fragile ecosystems. Yet despite this chaos, life continued to persist and adapt for a time. The true danger lay not in a single impact, but in long-term planetary change. Dust and aerosols from impacts may have slightly cooled the global climate. Combined with falling carbon dioxide, Earth's climate edged closer to instability. Ocean circulation patterns began to shift, altering heat distribution worldwide. Cold, deep waters expanded, reducing oxygen levels in some marine regions. Species adapted to warm, shallow seas faced growing environmental stress. Reef ecosystems, already sensitive, became increasingly vulnerable to collapse. Still, no single event warned life of what was about to come. Instead, multiple pressures quietly built up across the entire planet. Earth was approaching a critical tipping point in its climate system. When that threshold was crossed, change would come with shocking speed. And soon, the planet would plunge into one of the greatest ice ages ever recorded. As global temperatures dropped, Earth entered a massive glaciation known as the Hirnantian Ice Age. This cooling event began rapidly near the end of the Ordovician period.
The consequences were catastrophic.
Temperatures fell by over 14 degrees Fahrenheit, or about 8 degrees Celsius. Vast ice sheets formed across Gondwana, covering regions of modern Africa and South America. Smaller glaciers may have also reached parts of what is now North America. At its peak, ice volume reached nearly 60 million cubic miles, or about 250 million cubic kilometers. That is roughly 10 times the ice volume locked in Antarctica today. As water froze into ice, global sea levels dropped dramatically. Sea levels fell by over 410 feet, or about 125 meters. Shallow continental seas vanished, exposing vast areas of former seafloor. These shallow seas had supported most Ordovician marine life. Reef systems collapsed as water levels dropped and temperatures plunged. Species adapted to warm, sunlit waters suddenly faced extinction. Habitat loss occurred faster than many species could migrate or adapt. This marked the first major wave of the late Ordovician mass extinction.
Entire Ordovician food webs unraveled.
Entire ecological communities vanished as food webs collapsed.
From the inside out.
Many dominant Ordovician species disappeared within a relatively short time. Even powerful predators were not spared from the rapid environmental change. But paradoxically, the worst was still yet to come. After millions of years, the climate began to warm again. Glaciers melted and sea levels slowly rose once more. But returning waters carried deadly consequences for surviving ecosystems. Oxygen-poor waters spread across the oceans, suffocating marine life.
Even the resilient jellyfish.
This triggered the second and even deadlier extinction wave. Together, these two waves would devastate life on a global scale. When the extinction finally subsided, the scale of loss became horrifyingly clear.
A stark visualization of
An estimated 49
49
to 60% of all marine genera disappeared.
irreversible loss of life in the oceans.
Even more shocking, nearly 87% of marine families went extinct. Few extinction events in Earth's history reached such devastating levels.
Entire evolutionary
lineages were erased, never to return. Among the hardest hit were trilobites, once the icons of marine success. They lost roughly half of their known families during this extinction. Although trilobites survived, they would never fully recover their former dominance. Giant endocerid cephalopods vanished entirely from their apex positions. Their disappearance reshaped marine food webs across the planet. Reef-building organisms suffered catastrophic losses during both extinction waves. Brachiopods, bryozoans, and many coral groups declined sharply. Graptolites, once widespread, were reduced to only a few surviving lineages. Many planktonic species vanished, destabilizing entire marine ecosystems. The collapse rippled upward, affecting predators at every level. Even survivors faced dramatically altered environments and reduced biodiversity. Recovery would not be quick nor easy for life on Earth. Scientists estimate recovery took between 5 and 20 million years. Entire ecosystems had to be rebuilt almost from scratch. New species slowly filled the empty ecological niches left behind. Yet the world that emerged was fundamentally different from before.
What remains is a stark.
Many dominant Ordovician groups never regained their former prominence. The late Ordovician extinction permanently altered the course of evolution.
As life on Earth faced
Life
extinction,
survived,
new forms
but
of
only
creatures
by
emerged,
transforming into
adapting
something
to the
new.
changing environment.
And still, one question remains unanswered. what truly caused this catastrophe. Despite its scale, the exact cause of the late Ordovician extinction remains debated. Unlike later extinctions, no single trigger has been conclusively identified. One leading explanation focuses on
Earth's crust
continental
is not
drift
static.
and plate
Deep Venetian
tectonics.
currents drive the
During the Ordovician period, some
During the
450 million
Ordovician,
years
Gondwana
ago,
drifted
the
toward the
great
South
landmass
Pole.
of Gondwana began its slow
This movement likely promoted ice sheet formation and global cooling.
This unprecedented
Another
decline brings us
hypothesis
to the critical threshold,
involves
maintaining these
declining
levels is
atmospheric
paramount for
carbon
the restoration
dioxide
of global
levels.
ecosystems.
Lower CO2 weakened Earth's greenhouse effect, amplifying global cooling. The spread of early land plants may have contributed to this carbon drawdown. These simple plants accelerated chemical weathering of rocks. Weathering removed carbon dioxide from the atmosphere and oceans. Volcanic activity has also been proposed as a contributing factor.
The eruption sends vast
Volcanic
plumes of
eruptions
sulfur
may
into
have
the
released sulfur
atmosphere,
aerosols into the
failing to
atmosphere.
change the climate for years to come.
These aerosols can reflect sunlight, further cooling the planet.
In the
More
profound
speculative
darkness
ideas
of deep space,
look beyond Earth
the
itself.
possibilities are endless.
One suggests a nearby gamma ray burst from a hypernova. Such radiation could have damaged the ozone layer. Increased
The eerie light
ultraviolet
reveals the
radiation
silent struggle.
would stress
Increased ultraviolet
marine
radiation
and surface
forces
life.
these organisms to retract.
Another hypothesis involves a massive asteroid impact. The proposed deniliquin structure in Australia spans about 320 miles, or roughly 520 kilometers. If confirmed, it would be one of the largest impact structures on Earth. However, definitive evidence linking it to the extinction is still lacking. Earth's temporary ring system may also have influenced climate indirectly. Reduced sunlight could have reinforced long-term global cooling. Most scientists agree the extinction resulted from multiple overlapping causes. Together, they pushed Earth's fragile systems beyond their breaking point. When discussing mass extinctions, most attention goes to later, more familiar disasters.
The Cretaceous
Chief among
world
them is the event that ended the age of dinosaurs.
fiery messenger from the void.
The Cretaceous Paleogene extinction wiped out all non-avian dinosaurs. Its dramatic impact made it iconic, but its biological toll was comparatively smaller. Roughly 75% of species disappeared during the Cretaceous Paleogene extinction. The Late Ordovician extinction exceeded this loss in many ecological measures. Even the famous Permian-Triassic extinction is often misunderstood. Known as the Great Dying, it remains the deadliest extinction in history.
The
Up
scene
to
opens
90%
with a
of
close-up
marine
the empty
species
ocean
may have
surface,
disappeared during
reflecting
that
the dark
event.
and desolate atmosphere.
Yet the Ordovician extinction rivals it in ecosystem disruption and recovery time. The key difference lies in timing and visibility. Ordovician life was almost entirely marine, hidden beneath ancient oceans. No dinosaurs, no forests, and no familiar animals existed to capture imagination. As a result, its devastation feels abstract to modern observers. But scientifically, its impact on evolution was profound and lasting. It marked the first time complex life nearly collapsed on a global scale. Future extinctions would follow paths shaped by Ordovician losses.
Structural turning point in
Ecological roles left empty were filled by entirely new groups. This reshuffling set the stage for marine life in the Silurian period. Without the Ordovician extinction, later evolutionary pathways might never have existed. In many ways, modern marine ecosystems are built on its aftermath. The Ordovician extinction was not just a tragedy, but a turning point. It demonstrated how fragile even the most successful ecosystems can be, and how quickly Earth can shift from abundance to catastrophe. This ancient disaster carries a warning that still echoes today. The Late Ordovician extinction reminds us that Earth's stability is never guaranteed. Even thriving, diverse ecosystems can collapse under environmental stress. In the Ordovician, climate change unfolded without warning to living organisms. Temperature shifts, sea level changes, and oxygen laws acted together. No single species caused the extinction, and no single factor explains it. Instead, gradual changes pushed Earth's systems beyond critical thresholds. Once crossed, collapse occurred faster than ecosystems could adapt. Afterwards, survival depended not on strength, but on flexibility. Lineages able to exploit new conditions became the foundation of recovery. This pattern would repeat in every major extinction that followed.
The fossil record preserves this story.
The fossil record preserves this story with remarkable clarity.
Where layers of rock and fossils emerge.
Layer by layer, it reveals sudden loss, followed by slow renewal.
Emerging from the dark,
Recovery from the Ordovician extinction reshaped marine life permanently.
Rhinoids carpet the floor.
New predators, reefs, and food webs emerged in its aftermath. Yet, none of this erases the immense loss that came before.
Today, Earth
is again undergoing rapid environmental change.
reflecting the seriousness of the situation.
While the causes differ, the mechanisms of stress feel familiar.
structural turning point in
Climate shifts, ocean changes, and ecosystem disruption echo the past. The Ordovician teaches that gradual change can trigger sudden collapse. It also shows that recovery, while possible, takes immense time. Life endured, but Earth was forever altered by that ancient winter. The Late Ordovician extinction was not just Earth's first mass extinction. It was a warning written deep into the planet's geological memory. A reminder that life survives, but never without cost. You would never want to be alive when that lesson was first learned.
Life thrives.
Among the big five extinctions,
The Earth has
the Late
experienced
Ordovician
five
is
major
often
mass extinctions,
the least remembered.
but the first.
Yet scientifically, it ranks as the second most severe extinction ever recorded. Only the Permian-Triassic extinction surpassed it in total biological destruction. Unlike later extinctions, Ordovician life was almost entirely marine. This meant entire ocean ecosystems collapsed simultaneously across the planet.
450 million years
No
ago,
land
the
ecosystems
cosmos was
existed
vast,
to buffer the loss of
geologically
biodiversity.
massive, but biologically silent. A mass
When the
extinction
seas
event is
collapsed,
unfolding.
life had nowhere else to
Lack of
retreat.
oxygen is suffocating the ecosystem. The cold, empty
This
ocean
made the
stretches
Ordovician
out,
extinction
illuminated by
uniquely
microlight
unforgiving.
that casts a dim glow.
At first glance,
Many
Ordovician
dominant
appeared
groups
to be thriving.
vanished at the height
Yet,
of their success.
paradoxically, it was at this very peak
Evolutionary momentum was abruptly and violently halted.
In the wake of the
Recovery
Great Extinction,
required the
the
near-total
Silurians
rebuilding
seized
of
on
marine
land.
ecosystems.
These new organisms, like
The Earth once looked very different.
This process unfolded slowly over millions of years.
Changing over deep time.
The oceans that re-emerged were fundamentally different from before.
40 million years
New
after
food
the
webs
catastrophe,
replaced those lost
oceans
in the
are
extinction.
This is not mere
New dominant species rose from the extinction's aftermath.
now in the Silurian.
This pattern would repeat after every major extinction that followed. In this way, the Ordovician
Timeline
extinction
illustrates the Ordovician
set the
extinction.
template for
First
future
major event,
disasters.
Peak 1.
It revealed how planetary systems respond under extreme stress and how quickly balance can collapse when thresholds are crossed.
This is the
Long
Ordovician,
before humans,
a dynamic
Earth had already
by
tested
water.
its own limits.
Here, in the vast
The rocks remember what life cannot. Fossils preserve a silent record of sudden loss and slow recovery. The Late Ordovician extinction was Earth's first global biological warning.
A message has been received.
A warning written not for one species, but for the planet itself.
The urgency cannot be overstated.
This beautiful planet has
And it
endured
remains
some of the
one of the most devastating
devastating
events
life has ever known.
life has ever
reminding us
endured.
just how fragile it